So I now want to discuss non-experimental designs or quasi-experimental designs. And again, this is when we do not have all of those requirements to fulfill Mill's canons of causation. And again, these are not necessarily lesser designs, but if we can't do true experimentation, if we cannot manipulate the IV, if we cannot use random assignment, if we cannot have multiple groups to rule out confounds, we do still have some tools at our disposal to help us actually do a better study. So we're going to start with about the poorest, simplest design you can have. And that is a single treatment, single observation with a single group design. So in this case, all I am doing is I have no control group, I have no counterfactual, I don't know what would have happened if I hadn't used the treatment, and I don't actually even know what the participants were like prior to the treatment. I am simply assuming that my treatment is going to work and that I will find out that once I have given my treatment, I should find improvement. Now, a lot of times this is going to be in a situation where we can make a reasonable assumption that improvement is necessary. So for example, if you're working with a group of people that have never learned a subject, this is actually honestly most likely the educational design that you're most familiar with in classes. So the assumption is that you don't know a lot about advanced statistics. You're going to take various lectures with me, you're going to do homework, you're going to do lab assignments. That's the treatment, and I'm giving it to all of you. And then your first test is my observation. And when I get that test back, if most of you get A's and B's, I'm going to assume I did a good job, that you didn't necessarily know this material ahead of time, and that the observation shows that my treatment, my education, the classes I provided, my instruction, is what caused that increase. Now, I don't know that for a fact though. First, I don't have a pretest. So maybe you knew all this material before, and all I'm doing is telling you things you already know. And you would have done fine if you took the test without ever coming to one of my classes. Now, I believe that that's not the truth, but again, I don't know because I haven't randomly assigned half of you to not attend class and then give you that first test. So this is a relatively poor design. It is not a horrible design, and what I mean by that, it's still better than nothing. So if nothing would be no observation. I give a treatment and just assume it works. At least here, I'm measuring performance afterwards. And if I found, for instance, that I gave my treatment, I gave the test, and all of you scored poorly, we're talking F's, D's, and C's. At that point, I either have to ask, is my observation accurate? In other words, do I have a test that's too hard and doesn't cover the material? Or if I think that test is fair, that tells me something. Either you're very poor students, and I doubt that because you're in graduate school, or my instruction is failing and I need to change my intervention. So we can still learn from this design. Just recognize that our ability to infer any type of causation is extremely weak in this case. So the next one is simply adding additional post-test measures. And again, this is another way to think about, realize that when we have an X in one of these lines, it represents the application of treatment. And then afterwards, if it's not shown again, then we're not continuing treatment. So this isn't necessarily indicative of this class. If this was indicative of this class, what this would look like would be X01, X02, X03. Treatment, education, test 1. More treatment, more education, test 2. Treatment, more education, test 3. This is basically finding out, simply asking the question, if the treatment did have an effect, and again, we don't know that for sure because we don't have a control group and we don't have a pretest, can we at least make the assumption that the treatment lasts? So we'll often see this more in clinical settings, maybe educational settings, where I give a treatment and I give that first test, but then 2 weeks later I give another test, and 2 weeks later I give another test. In other words, if the treatment really did have an effect, and again, we don't know that for sure, we'd expect hopefully that the education would stick. We'll also see this sometimes in organizational settings where, for example, a group may be given a training on how to work better in groups and teams. Immediately after the training, they're given an assessment. Did they learn these skills? But then maybe 3 months out, they'll be given a second assessment. Are they still using these skills and do they still know them? And maybe then again at the end of the year, they may be given a third assessment. So this is really not necessarily adding components to answer any questions about can we actually say that the treatment caused the effect. This is adding observations to at least say that if we are correct that the treatment did have an impact, does that impact last over time? So the next design is we're starting to get a little bit better at answering some questions without experimental design, and that is the one group pretest post-test design. It at least adds a pretest. It provides a better effect estimate. Still doesn't control for confounds. There's a lot of confounds that can occur in this study, but at least we know what were people like before the treatment versus what they were like after the treatment. And often the biggest confound of this kind of a design is actually time itself or the exposure of other treatments. So this basically means if I did this in this class, I would actually give everyone the first test day one before any intervention and grade them. And then I would give you the next 3 to 5 weeks of education, lab assignments, homeworks, and then give you that test again. And now I could say, well, before my intervention, I knew they didn't know this material because they did very poorly on the test. After my intervention, hopefully, they did very well. I've got a stronger argument that my treatment is at least doing what I think it's doing. Now, it doesn't get rid of all confounds. It doesn't say what would have happened without the treatment. You're all in grad school. You're probably all meeting with advisors. You're taking other classes, and those other classes may be hitting on some of these issues as well. But it at least makes an argument that there was a difference between before the treatment and after the treatment. Now, as we move forward, we start to just get to more and more complexity of designs, and we're still looking at one group design. Now, here's another one that we can add even a little bit more that can start to make a stronger argument that the treatment is actually doing what we expect it to do. Now, in this case, we're introducing and removing a treatment. This works best if the treatment itself is not expected to have a long-term effect. So a lot of times this may be a treatment that is needed daily. It may actually be a drug treatment, for instance. So it's something that if you removed the intervention, you would actually expect people to start doing poorly again. So the intervention needs to stay to keep the effect going. So this is basically a remove treatment design. We do a pretest, we add the treatment, we do the post-test. Now again, if we find that as we add the treatment, that post-test goes up, we see a significant increase in the scores from observation 1 to observation 2, we start to have an argument the treatment's having an effect. But we don't have a control group. We don't know for sure. This doesn't tell us for sure, but it adds to the effect. If I then remove the treatment and then do a third observation, and what I find is a pattern of low score at time 1, higher score at time 2, and then back to a lower score at time 3, that starts to make a stronger argument that that treatment is having an effect. Because now we have both evidence that it caused an increase, still potential confounds, other explanations, but also when we removed it, we found the effect disappeared or reduced again. So again, we can start just kind of adding to this. This is again single group designs, but the more time you have and the more resources you have, the more we can start doing a repeated treatment AB design. This is introducing a treatment, removing the treatment, and reintroducing the treatment. And again, this needs to be something that is a treatment that would not be expected to have a long-term effect. If you've got a treatment that you expect one application of that treatment should help the person from then on, this is not the design to use. But you can see that we've now got an observation, pretest, a treatment, post-test. We remove the treatment, another post-test. Then we bring the treatment back and we have a fourth post-test. And again, the pattern we're expecting there is low at time 1, high at time 2, low at time 3, and back to high at time 4. At this point, it starts to become pretty hard to argue that anything other than the treatment is co-varying with these applications and removals of treatment in a way that would be affecting the outcomes. Now, we can also add what's called a calendar recall pretest, and realize a lot of organizations will do this when they don't have the time or resources to do an actual pretest, but they ask participants to self-report behavior before the treatment. This will often happen in clinical settings, for instance, where someone might come to you with a drinking problem or depression, and you ask them, how depressed have you been in the last month? How much drinking have you done in the last month? You're not actually measuring it in real time. You're asking them to recall the past. This is still better than not having any pretest, but recognize again, ideally pretests should be measured the same way our post-tests are going to be measured, kind of in real time. So now we can start looking at groups without true pretests, but at least with a comparison group. So this is a for the first one is a post-test only design with non-equivalent groups. So notice I've got an NR listed here, non-random. We could also just put an N here. But basically what this means is that I'm looking at a group. I have a single group design, but I have access to another group. So it is weak. It doesn't add much, but at least it can make an argument. So this would be an example of I am working on an intervention to improve math skills in my 3rd grade math class. So I change my curriculum, I do the intervention, and then I test math scores, and I find fairly decent scores. That's fine, but I might want to make an argument, well, how are other classes doing? So I might ask my fellow instructors who are teaching other math classes, would you mind sharing your test scores with me? So that's a non-equivalent group. It is a control group because they're getting more standard education. They're not getting my new curriculum, but there might be a lot of other differences, including just who the kids are in that class, teaching style, testing style, etc. So again, this is just another tool we can add, is that if you don't have access to randomly assigned control or placebo groups, you can look within the organization to find out, is there non-equivalent groups that I could at least make an argument of, here's what it looked like when there wasn't a treatment, at least with different people. So again, we can then also do post-test only using independent pre-test samples. So this is an example where I actually have non-randomly assigned 2 different groups. Let's say they're 2nd grade. So in the 2nd grade, I'm doing a treatment versus my class versus someone else's class and observation 2. But I'm also looking at how did those classes vary last year as 1st grade students. So for example, if I find that my math class in the 1st grade and Dr. Simpson's class in the 1st grade had almost equivalent scores. In other words, there was no difference between our classes. And those same students are now with us in the 2nd grade, and I'm doing a new intervention. That starts to make a stronger argument that these groups were relatively performed similarly on a similar level of math skills in the past, and therefore, if I find a difference in today's study with my intervention versus that class that is a non-equivalent group, not randomly assigned, but I still have that pretest data. Again, it's giving us more information. It adds a pretest from a different sample or from the same sample but different people. It's basically looking at that past. So the other thing I could do is, again, it's different people this time. I look at the test scores between me and Simpson's class in the 2nd grade math class last year. There wasn't a difference. Now it's new students in our classes, but I'm doing a new intervention. So these are different ways we can kind of think about how can we try to get closer to a control group or a placebo or counterfactual group, even if I don't have access to random assignment. Now again, these are not as good as true experiments and random assignment, but the more we can think about these, the more we can include these, it gives us some tools, especially in applied settings, to make better studies. We can also use post-test only using proxy pretest. The proxy pretest is similar but not the same. So treatment's effect is not as clear as when using true pretest, but avoids a testing effect. And what testing effect is one of the problems is remember I mentioned earlier that if we really wanted to do a pretest post-test design, I would have to give you test 1 at the start of the class. But that also means you now know exactly what test 1 looks like. You are going to be better able to study for it, and you've been exposed to it before. So some of the improvement in the score may have nothing to do with my treatment. It may simply be the fact you've seen the test before. So this would be actually trying to get around that. So we weaken the effects of the pretest by creating a proxy pretest. So in this case, I would give you a knowledge test on basic statistics that is not similar to the actual test. So in this case, it's observation A1, meaning form A, treatment, and then observation B2, second form, different test. So again, that alone would be a proxy pretest, post-test design, but I could also then add a non-equivalent group. For example, if I was changing how I was teaching Psych 520, maybe I'd look at last year, and I'd look at the pretest that I gave then, form A, their performance on test 1, form B, and look at the improvement, and then look to see is there a better improvement this year between the pretest, proxy pretest A1, and the actual outcome B2. So again, the letters are simply representing that though the observations are meant to capture the same construct, they are different forms, different tests. And again, the number is simply when that observation is being used, time 1 and time 2. So we can also use control and pretest. So we can use an untreated control group with pre and post test. This is probably the most common quasi-experimental design when possible. It's simple, but still the best components of the previous designs. The big thing here, though, is we have a non-random situation. So we might be looking at the difference between men and women. So we may be giving intervention to men versus an intervention, not an intervention to women. This may be class 1 versus class 2. So again, however we're defining the groups as pre-existing, but then one of those groups is getting a pre-test, an intervention, and a post-test, and one of those groups is simply getting the pre-test and post-test with no intervention. Now again, we can start playing around with these ideas. We can use a double pre-test, same design with 2 pre-test observations. So remember, the more observations we have, the more certain we can be of the stability of that score. So again, just looking at this top line, so again, we're on the first set of notations, NR 01 X 02, NR 01 no intervention 02. We could add 2 pre-tests and 2 post-tests. So I do an observation 1 and 2 prior to the intervention, both in the control group and the experimental group. And then I could also add post-tests. So it could be 01, 02, X, 03, 04, showing stability prior to the intervention and stability after the intervention. And likewise, in my non-equivalent control group, I could have observation 1, observation 2, no treatment, observation 3, and observation 4. And what I'd be looking there for support of my hypotheses is that in the bottom group, the one without the intervention, all 4 of those tests, pre-test and post-test, should be very similar. In the actual experimental group, time 1 and time 2 pre-test should be very similar, and time 2 and time 3 and 4 post-test should be similar but higher. Those should be the 2 that are significantly different, but should still be similar to each other. We can also then do switching replications across non-equivalent groups, and this is a design we'll often see in applied settings. So for instance, you may be talking to an organization about a new intervention to help with math skills with kids. And they're like, well, you've convinced us it's going to work. That's why we're letting you come in and do it. But why shouldn't we give it to all of our students? And you, of course, say, well, I want to do an experimental design. And they're not as interested in the science because if you convince them it's worth their time to test it, they want to see all their students get it. And this particular design can allow for that. Basically, it makes sure that every child or every participant in the study does eventually get access to the actual intervention, but they get them at different times. So for example, group 1 gets pre-tested, they get the intervention, then they get the post-test, and then they get a second post-test. Group 2 gets basically gets the pre-test, no intervention, the second test at the same time as group 1, and then gets the intervention. Now again, what the pattern we're looking for is we'd expect in the top row a low score at 1 and higher scores at 2 and 3. And in the bottom group, we'd expect lower scores at 1 and 2, and then a higher score of 3. And if we found that pattern, that starts to make a much stronger argument in a non-random, non-experimental design that it is the intervention that's having this effect. So we can also use matching. So I've been talking about non-equivalent designs, and usually when I refer to non-equivalent designs, I'm talking about basically convenience samples, people that we don't have random control over, we can't assign them to groups, and we often assume that they are very different, but we can make efforts to match them in quasi-experimental design. So we can use that post-test only. We can use that for matching or stratifying. In other words, we might actually use a post-test to make the argument that these 2 groups are similar because there wasn't a difference between them on our observation, the post-test, before we did the intervention. If we find there's a difference, we may actually then, instead of comparing the whole group to the whole group, we might do a stratifying, basically blocking or subclassification. So if, for example, if one group only had 2 A students and the other group had 5 A students, instead of just looking at the averages of the total group, we might compare A students to A students, B students to B students, C students to C students, etc. Matching or stratifying occurs on non-random assignment to condition, and we can match on pretty much almost anything you want, but generally speaking, what you're trying to do is you want to match on variables that could be confounds. So if you're interested in looking at academic achievement, you want to pre-test academic achievement to make sure that there's not a difference between your non-random groups. So there's a lot of different types of matching. One of them, for example, is exact matching. So again, We can look at the group matching. Do the two groups have statistically significantly no difference between their performance on a post-test or pre-test? Or we could do exact matching. In other words, the only way we're actually going to compare two people from our non-equivalent groups at the end in our observation after treatment is they had to have the exact score in the test. So if I had a 1 to 100 score test and I had a participant in group 1 that had a 99 and a participant in group 2 that had a 99, those would be two of the people that I would include in my study. But if I had someone that had a 97 in one group and no one scored a 97 in my other group, I would drop both participants from my analysis. Now, that often results in you losing a fair amount of participants, and a lot of places will use various techniques, and here's just a few of them, to basically do caliper or distant matching, and that's one of the things I was kind of referring to in the last slide. I put all the A students together, all the B students. Now, there are more advanced ways to do matching, and we will get into some of these cases in the future. One of them is basically, especially if you're measuring multiple pre-tests. In other words, let's say you're actually wanting to match on not just academic performance, but also social economic status, year in school, and gender. We might put all of those together to find basically clusters of students that are very similar on all those traits. That would be what's called a multivariate or Macaninobis matching. We often will see more like greedy matching, and what greedy matching is we basically just try to come up with the best matches without losing any participants. There's other techniques that we could also talk about as well, and we will get into them. The biggest thing I want you to really know about here is the difference between exact matching. They have to have the exact same scores. In other words, they're not, or they're not used, versus caliper, or distant matching, where we basically try to make sure that we use as many people as possible from our sample. So full matching matches multiple controls to each treatment unit, multiple treatment units to each control, and full matching is exact matching. We may lose a fair amount of participants. So the problem with matching, we may not have a match for all units. So again, we may lose some participants. There is a tendency to regress to the mean. That means that whenever we measure anything, anyone that scores extremely high or extremely low, and remember, we're using those scores to match them to someone else, has a tendency to do better if they scored very poorly, or worse if they scored very well the next time they take a treatment. So we do have to worry a little bit that if we're using exact matching and someone has a high or low score, they may or may not have a different score afterwards on the actual post-test. We also may do undermatching. In other words, we may match on some variables, but not others that are important to the study. And again, if we're trying to improve matching, we're generally wanting to try to find groups that are very similar to begin with. So if I was trying to match seniors versus freshmen to how they react to an actual intervention on educational attainment within a class, that would be harder than trying to match freshman to freshman. We want to match on stable variables. We want to match on variables that are unlikely to change greatly other than our outcome. And if possible, we want to match on aggregated scores, group means, or individual scores across multiple predictors. And one of the ways we can do this is something called propensity scores, which basically creates an individual ranking score for each participant on multiple outcomes or multiple predictors. So again, we measure not just academic performance, but maybe gender, academic performance, SES, and we create a propensity score for each person based on the aggregate of those variables, and then we match those propensity scores. So people with very similar propensity scores will be matched together. And again, once we create those propensity scores, we can do exact matching. People have to have the exact same score, or some form of non-exact matching, such as greedy matching, where we basically create bands or groups. As long as you're in propensity scores from, let's say, 30 to 35, you're going to be put in the same comparison group. Again, kind of like A students versus B students. So again, we want to use the many elements of experimental design to create better studies, even when we can't use true experimentation. We want to ask how many pre-tests and post-tests are necessary. And again, the more tests, the clearer the pattern, but more attrition. So people may leave your study because they're tired of being tested. More time, so every test takes time. So as you have multiple pre-test and post-test, you're usually talking about a longer study. You are going to get test fatigue or people becoming familiar with the test as they're being tested over and over again. And finally, just the resources of giving and scoring all of those tests. Again, if possible, we want to use comparison groups. We want to use those comparison groups, especially if pre-tests are not practical, but often with pre-test as well. So the comparison group will often allow us to reduce the amount of testing necessary and can improve generalizability by, again, giving us at least a theoretical counterfactual, what would happen without the treatment. And finally, can we vary the number of times and when the treatment is being given? So how can the same treatment be tested differently? And does giving the treatment have the same degree or effect as removing the treatment? And can we therefore use treatments as elements to help us understand the actual nature of the relationship we're looking at, again, when we can't use true experimentation? And this really is important because pretty much all of you are planning to go into some field that is an applied field, where you're going to be working in organizations, within schools, within companies, and even with clients and patients, where you're probably not going to have access to true experimental design. You're going to have to come up with good quasi-experimental designs that fit the requirements of science. Can you really say that what you're doing is working within the restraints of practice? So again, using these many elements, we want to add controls or measures to improve the validity, the truthfulness of our findings by reducing other possible causes. So we're using all these elements to try to address questions of what if you're wrong? What are the other explanations? It also increases the complexity of the statistics, however. So it does use more resources, more time. Longitudinal studies increase history effects, attrition effects, and maturation effects. So again, if I'm doing multiple pre-tests and multiple post-tests over a long period of time, one of the potential confounds I'm introducing is history effects. In other words, things that are happening to your participants that have nothing to do with your intervention. Attrition effects. Certain people may be leaving the groups. So for example, you may have more people leaving your treatment group because it takes more time and effort than the people that are in your control group. And finally, you have to be at least aware of the potential of maturation. In other words, just natural improvement or natural decline over time, especially in very young and very old populations. When we're assigning people, assume non-random assignment is always going to be biased in some form, and that's one of the reasons we use the elements to try to address some of those biases. We're going to control biases, again, for non-random assignment by using additional elements, matching, stratifying, and covariating. In other words, we're going to add additional pre-tests, post-tests, and non-equivalent control groups to try to make an argument for that there really is the effect we're finding. Selection bias is problematic if we don't know what caused the selection into conditions. So again, if we actually know, for example, that we're comparing high performers to low performers, they are going to be different groups, but we at least know what the difference is, and we can statistically adjust for that. And we'll be talking about some of the advanced techniques to adjust for this actually in year second class of this, 521 next semester. And the big problem with any of this is if we're not using random assignment, if we haven't controlled IVs, no matter how many tools we use, no matter how many components we create, there's always the potential that we miss something, that there is still a hidden bias or a hidden confound that we did not account for.